Okay. So we're looking at a worked example here, which you have a copy of. It's in your Show My Homework for today. So the reaction that we're interested in is dinitrogen pentoxide, which will break down to make oxygen and NO2. And we're told that 0.8 moles of N2O5 is started off, and then we end up with 0.96 moles of NO2 at equilibrium. Okay, so that's the beginning of our ice table right there. So we have NO2 going up by 0.96. We're assuming that it started at 0. There we go. Remember, your change line and your ice table has to be in the same ratio as your balancing numbers, 2 to 1 to 4. So if that's gone up by 0.96, then that must have gone down by half as much, 0.48, and this must have gone up by a quarter as much, 0.24, and that gives us our final line there. 0.32 moles of N2O5 are left over, and 0.24 moles of oxygen have been made. Okay, great. So our first job is to work out the total number of moles. That's just simply adding up all the moles that we've worked out together, and that comes to 1.52. And now we can work out the mole fractions. So a mole fraction for each substance is the amount of moles that we've made divided by the total number of moles there. So 0.21, there's no units here because it's a mole fraction, just a fraction of the total amount. 0.24 over 1.52 is 0.16, and NO2 lastly is 0.96 over 1.52, which is 0.63. Notice, if you want to check, if you add these three numbers together, the total of all the mole fractions has to add up to 1. By definition, if you add up the fractions of all the different moles that make up the total system, they must add up to the whole. Okay, so now we're in a position to work out our partial pressures. So partial pressure is defined as the mole fraction times the total pressure. Well, in this example, the pressure we're given is 250 kPa. So let's work with that. So N2O5, so my mole fraction is 0.21 times 250 is 52.5. For O2, it's 0.16 times 250, which is 40. And for NO2, it's 0.63 times 250, which is 157.5. Okay, these are all in the same units as your pressure. So if the pressure is given to you in kPa, then these will all be in kPa. All right, next we need our expression for Kp. So Kp is products over reactants raised to the powers of their balancing numbers. So partial pressure of oxygen times the partial pressure of NO2 to the fourth over the partial pressure of N2O5 squared. And now it's just a question of doing some button bashing. So we've got on the top here, oxygen is 40, pressure of NO2 157.5 raised to the power 4 over N2O5 is 52.5 squared. And if you bash that in, it comes out as 8.93 times 10 to the 6. For units, well, we can do the same thing. It's kPa times kPa to the fourth on the top, kPa squared on the bottom. I've got kPa to the 5 on the top and kPa squared on the bottom, so that cancels out as kPa to the 3. Again, if we had converted our pressures to pascals, the numbers would be basically the same but raised to a different power at the end. I'm not going to work out what it is, but you get 8.93 times 10 to the something, and your units would be pascals, but there's really no need to do that unless you're asked to do so. And then the second part of the question, that was all A. The second part of the question asks, what would happen if you increase temperature? Well, we're told the reaction is endothermic. If I increase temperature, that shifts the equilibrium position towards the endothermic change, which would be forwards to absorb the extra energy. So therefore, I would get a higher yield of products. And since the products are on the top of the expression for Kp, Kp will increase. What happens if I increase pressure though? Well, as we know, an increase in pressure shifts the equilibrium to the side with fewer moles of gas, which is the reactants. So the equilibrium position would shift to the left, which means there's there's more N2O5 in the system. So you might expect Kp to decrease, but remember Kp is the equilibrium constant, and it's constant for a given temperature for a given reaction. So no amount of changing the pressure or changing concentrations will ever make a difference to Kp. It'll change the equilibrium position, but not Kp. And that's often very confusing to students because they feel that Kp really should be changing there. The only thing I can tell you is I'm sorry. Just learn it. Kp is a constant at a given temperature. It does not change for anything else.